Okay, so today we have 5 presentations. So just note that the comments and your votes are due at noon tomorrow. So comments and votes are due at noon tomorrow. And today we have 5 presentations, and I just put it in a chat. So the William and Thomas and Michael and Colin and Luke. And each presentation should be within 15 minutes. So I will notice the 1 minute before the presentation. 1 minute before 15 minutes. 1 minute before, yeah. Okay, so I think Bill, can you share the screen? Or if you cannot, just let me know. I will. And also Luke, can you send me the presentation file to me by either email or to Canvas?
Yeah, of course.
Yep. Okay, so let's start. Yep. You're muted.
Thank you.
Sure.
Let's try this again. All right. So daily temperature time series analysis. The main thing, this dates back to last semester where I started working on this in 5030, but I got into deeper and was going to extend a little further, but the analysis and the issues with the analysis ended up, I stayed completely into the original structure, except deeper work. So the question that started it was, can global warming, climate change be detected by local temperature records over the current span of my life? A little over 60 years. My goal is to determine how easily the climate change could or should have been detected over my lifetime. In addition, use the analyses from this class, 5820, to refine the results further. Can I determine a climate trend? If it's significant in 60 years, what's the inferred future temperatures? I used linear regression and other regression models, and let's go to it. The data came from the National Oceanic and Atmospheric Administration, NOAA, historic databases, the LCD. It's a bit of a pain to get because you can't get more than 9 years at a time. So, and until you've received that and download it, they won't let you do another set. So it takes about 2 or 3 hours to get down an overall process. This particular one has my data currently has a little over 2 years missing, and plus a handful of missing days. But the number of days and data points I had was over 21,000, so I really didn't see that as a problem. The second thing is I had the ability initially to do it via up to and including time hourly. And since I'm looking at a very large scale, I ended up using the average temperature of the individual day. So I reduced my volume dramatically. And so what did I choose? Well, I chose Detroit Metro Airport for several reasons. It has a near continuous time collection over the time range. It's been that or Willow Run has been around a long time. I expect to see some temperature moderation from the Great Lakes, and it's close to where I've lived most of my life. So when you take a look at the analysis of the data, it starts off looking like this. And it's a time, as time series data, you develop problems if you do scatter plots, because it's sequential, it's time spaced. So to make my analysis better, I operated from a days from, back up. I operated from a days from a given calendar date, of which I used January 1st of 1960. And so this allowed accurate placement of the time plots and easier analysis. I didn't go into a lot of factors. I used basically time to initially to go over the entire population and to select annual dates to see how this would go. With discussions with Dr. Schinke, one of the things is that time series cannot be randomly analyzed. If you go through this plot right here, I call a one-off, which is, let's look at the correlation or the auto correlation that is in this data up top. If we take each day and then compare it to the one following it, so you go or basically one off per day, you get a very long correlation plot. This is very stretched. Okay, what do we do? Well, I'll be getting through into that a little bit further. So I ended up simplifying, because with the data the way it is here, I ended up testing 3 different models to see just exactly what I would get out of it in deeper type runs. One was linear. With all this variation, you get a green line. Then you have cyclic, which is sinusoidal, and then I combine the 2 into a single run, and you can see the slight variation between the red and the blue. The red is canted similarly to linear, and the blue goes straight down. Here's my results of the 3 basic tests. You got linearity, you got cyclic, and you got linear cyclic. The 2 things that immediately stand out when I look at the residuals and the one-off correlations of each is, first off, this doesn't seem to change much from the original data. What it did was it basically flattened it out. Instead of having a slight slope, it pretty much is straight on. But still a lot of autocorrelation. Then if I go straight with cyclic, it massively cuts the variation. And you can see that the one-off error correlation gets tighter also. And when you combine them both with the model, which is still not a bad model, this flattens out, and it just slightly, you can see the correlation goes from 0.9 to 0.71 to 0.7. So this is not horrible autocorrelation in my opinion. Okay, so and it was fascinating on that. If you want to do cross-fold validation, don't. Because of the random area, the random distribution does not work. It works against the time sequence. So instead, any folds you do must stay in sequential order. So I ran 2 different 12-fold analyses against the 3 models. And I got, for the first one, I modeled it and ran. So getting some graphics to clean up a little bit ended up being bad. But if you just run the diagonal across, 1, 1, 2, 2, 3, 3, that is the model that I used. It was a 5-year chunk of data, and I cut it up all 12. And so there was like 1,766 elements per chunk. Now, there's a lot in here. I just found it fascinating how the RMSE, and I used root mean squared error instead of MSE because that gives me a common temperature. So I'm looking at a change in Fahrenheit. Therefore, this tells me I have a variation of 18, root mean squared of 18 degrees Fahrenheit. But if you take out the annualized cyclic pattern, it gets cut even well past half. Going down into the cyclic, it has a little bit better, but so that's where that stands. And then the second one is called forward chaining. This one is interesting, in which I didn't quite explain it the way I wanted to, but you start off with the first chunk, and then so chunk 1, and then you do the model, you do the testing against chunk 2. Then you go test chunk 1 and 2, and you get the model, you test against chunk 3, all the way through chunk 11, and then you test with chunk 12. So that's why they're slightly off skew. One's the RMSE, and the other one is the trained data. And the trained data expands as we're doing the job. Now down over here, you'll notice again, it drops down, and something's going on in here. For all the data I have, you still get a bit of an up, something weird going on over here, and I haven't quite figured out what that is. But overall, the line still looks pretty good. So forward chaining is a very significant way of doing analysis, not cross-validation, but very close to it for time series. Okay, now if I wanted to try to establish the line of change, or the mean increase, I remove the cyclic portion only and ran several different points. LM minus cyclic is a straight line. That's the one we started with. A natural spline at 61. 61 happens to be the number of years that we used. It's very noisy. Natural spline spent over 4 years. It helped balance a little bit. Smooth splining at 16, smooth splining at 8, and then the original temperature span at purple. So basically the black and the purple pretty much parallel each other, slightly different. Then with all this, you can see how it works in the residual plot of just removing the cyclic pattern that we already established. Now, the important part next comes down to forecasting. If you wanted to take a look and say, okay, linear minus cyclic, I didn't go and add the other very variable stuff. I'm trying to decide whether I should have or not. But to be honest, linear and minus cyclic ends up giving us a very consistent, and I have no idea where it becomes a major problem. But can we forecast temperature change? The answer says yes. Is it showing up as anything? Yeah, it could be a problem. Increase of almost 10 degrees over the course of 100 years. In summary, data analysis does seem to show climate change exists, at least in the Detroit area and over the recent past. Most of the models point to increasing temperatures over time. The main strength of this analysis is the large number of temperature samples. The main weaknesses I have so far are small time span geologically. Modeling with the start further into the past could help if it's the change is cyclic or this behavior is man-generated, and a restricted location. Adding analysis to say the Great Plains, the East Coast, the West Coast could reduce the likelihood of a localized phenomena. Future steps for me is to analyze temperature changes with respect to altitude, how high off from the sea level, location, latitude, longitude, and local environment, dry, around a lot of water, mountainous. Then perhaps get a chance to analyze other aspects of weather. How much rain, how much cloud cover, how much sunshine. And then one of the fun ones that was just brought up while I was talking is, what is the probability of rain greater on the weekend? And with that, I'm done. And on time.
Sure. Well, thank you, Bill. So
Questions?
Does anyone have questions?
I will tell you, this was to do the looping structures and to do a lot of the Dr. Schinke has a huge amount of background data from my stuff, but it is. I spent more time trying to debug the code than doing hardcore analysis. It was driving me crazy. Any questions?
Did you have to include any like white noise in any of your models?
No, there's all of that is white noise directly from natural phenomena. I have at some point, Colin, if you wanted, I'd send it to you. But I took a lot of looks at the residuals and tried to see if I could do something. Once you take out the common patterns, can I see something with the residuals? And part of what I was looking at when I was pointing out that last bit is that supposedly, but I can't see it in my stuff, in my data, supposedly there's a hockey puck in temperature. We're going up faster now, supposedly, but I haven't been able to prove it with my data. So that was part of the reason I wanted to get more data and do some more analysis on that. Okay. Any other questions? And did I answer that question? Answer it for you, Colin?
Yeah.
Okay.
Thank you.
No problem. Anybody else? I guess I'm done.
Okay, thank you,
Anything
Bill.
from you, Doctor?
So yeah, so the many statistical models and also machine learning models assume the independent observations, but typically time series data are not independent. And William removed some cyclic component, linear components, but still the correlation exists between adjacent observations. So that is 0.7 for the adjacent observations. So for forecasting purpose, still you can apply any models. But if you do statistical testing based on IID assumptions, that result is not accurate. So that is what we have to care about. Yep. Okay, thank you. So the next one is the Thomas. So can you share the screen?
Yes, I can. Okay, can everybody see it?
Yes, you can start. Yep.
Okay, so my project was about an experiment that was run about detecting a reversal, about human beings' ability to detect a reversal of time, right? And what some of the objectives I wanted to do were see if some people are better at detecting a reversal in time than others. If there's situations that are easier to detect a reversal in time, and and compare basically classifiers. And I unfortunately didn't get a chance to do SVM, support vector machines. So the data used for this project was from the following paper. It's ready to detect a reversal of time's arrow. It's a psychophysical study using short video clips and daily scenes, and it was found in on the website Data Dryad. So there's actually two data sets. Oops, didn't want to click that. Right? There are actually two different data sets because the experiment had, or the paper talks about two different experiments. Right, the first experiment had 10 adults, right, and they watched a total of 360 video clips that are around 3 seconds long, right, and there are various, they were of various like real world activities, so like closing a door or walking forward or something in free fall, right, and they're all found from moments in time data sets, so it's a big repository. Right, and the participants were seated and asked to judge whether the video clip was basically played in forward or reverse direction. So after moving NAs, from the data set, there was 7,090 rows in 5 columns. The two columns were used to just indicate the video ID and the participant. And the other 3 columns were whether the actual clip was reversed or not. So the actual direction, the participant's prediction, whether it was reversed or not, and the time it took, so their reaction speed in milliseconds. Right. So this is a box plot between forward and backwards in terms of actual time. So the reaction speed on average between actual time was around the same, whether the videos were replayed forward or backwards. And they were fairly accurate in terms of predicting, because this is participants' prediction versus actual direction. They were fairly accurate in terms of predicting this out. Right. The second experiment, which was where most of my analysis was done, it was actually done with 27 new adults, right? And it took 120 of the 360 video clips that were originally used in the first experiment, right? 66 of them were video clips that in the previous experiment, all 10 participants had perfect judgment on. So they, in terms of forward and backwards, they judged it correctly. 54 of the video clips were where the correct judgment weight was less than or equal to half. These video clips were then divided into 10 or 11 parts, 9 frames each, and the participants were asked to judge, once again, the direction and respond in a period of 2 seconds after each presentation. Right? So this second data set had 230, after removing NAs, had 2,370 rows and 98 columns. And of the 98 columns, 91 of them were of a strength of evidence measure. And so the README file, when you download these video clips, are very vague about what this evidence means, and they're just like abstractly labeled. I spent a lot of time trying to figure out how they came to these variable labels, and I couldn't figure out how to make sense of any of them. But what happened, while reading the paper, what happens was they took all the participants' individual judgments about whether the small like 9-frame segment was in forward direction or backwards direction. If it was in forward direction, they assigned basically a +1 to it. In a backwards direction, they assigned a -1, right? And then they summed them. So it became like it's the evidence was basically just the 91 evidence variables was just basically a measure of how strongly the participants thought a given segment discriminated between forward or reverse condition. Right. So in this segment, so the first one is forward in versus backwards, this first box plot, in terms of reaction speed, but it's of actual measure. why. The second one is of the ones that the participants, their prediction, right? In this case, the sorry, my cat is in this case, the backwards, they were significantly faster. And this because, to kind of answer my question, the evident, when they chose the evident, they noticed in the paper that when the evident videos, there were like ones that had to do with like forward motion or free fall or diffusion had, they were very quick to tell. So they had like a natural direction to them. So people were very quick to decide that that's in reverse order or forward order. So this is why it's different than the first experiment. So this is a correlation matrix. And as you might expect, since all the evidences were kind of constructed out of their individual measures, they're all kind of correlated together. So for analysis of like comparing the regression model, I wanted to compare logistic regression, LDA and KNN. I didn't get a chance to do support vector machine. And how well we could predict the actual direction. After removing NAs, I ran a logistic regression and selected all the variables that were significant, statistically significant, because with 94 variables is just too much. And then ran backwards AIC to further reduce the variables. And this step ended up removing only 2 variables to end with 15, right? Then I ran the logistic regression with or without loss penalty, the LDA, and then the nearest neighbor for k equals 10. Right. And these are the results. The accuracy. So first of all, just to answer my question, the 10 participants in experiment 1. So the first row is accuracy, and the second row is error rate. Right, and there was a significant difference between how well, this is from the first experiment, how well they could actually predict a reversal in time. Right? So, and the mean was, oh, that's from a wrong spot. I think I missed a comma. So the mean was supposed to be 0.076. Right. And then I calculated the accuracy of, for every video ranges. Oh, most of my analysis has to do with experiment 2, but there was a problem in, so this has to do with experiment 1 data. There's a problem with the data and how it was coded, where in the paper, they said they had 27 individual people that did the experiment, but the variable that was listed underneath there for participants, the label only went from 1 to 10. So I don't know, they're like counting the same, like 3 people as the same. So I didn't do this analysis with the second experiment because I didn't know how to handle that. Right. But there was a significant difference between the type of video in terms of the ability to predict time reversal, and that's some of them they couldn't basically predict it at all, and some of them they were perfect basically. And in comparison between the models, LDA had the best test accuracy at approximately 79.2%. And then KNN with k equals 10 had the worst accuracy, 66.8%. Right. And these are the contingency tables for the 4 different models. Right. So in summary, yeah, people's ability to detect time reversal varies, and yes, there's easier situations to be able to detect time reversal, like free fall, forward motion, and diffusion process. The best predictive model was LDA in terms of accuracy. So in conclusion, or further investigation, I would like to try to classify it with SVM. A way to run the analysis with participants as a factor variable, either like just focusing on experiment 1, or somehow try to figure out how they code the second experiment to run that as a factor variable. And the thing kind of really interests me is experimentally, if like there's this strong time reversal detection for things like forward motion, wonder if that would disappear if the object in motion was something very symmetrical, like a sphere. Whether like if there's enough, if it's really, if you could still have a strong time reversal detection if there's no like natural orientation to the object. So, and that's the.
Okay, thank you, Thomas.
Oh.
So does anyone have questions?
I have two.
Mm-hmm.
Thomas, first question. Do you think you could have merged the data sets? And or would that have shown up kind of a bimodal behavior, or do you think they were consistent enough to make a super analysis? Or were they disparate or different enough that it would be difficult to do so?
So there were very different types of analysis, because the ones were over the whole video segment, while the others were each data point was over just a like 9-frame segment.
All right, that'd be fine. When you trimmed out the variables, were any of them? Were you surprised at any of the variables? I didn't get a list of what the variables were.
Yeah, well, that's because they're just all evidence measures. I have no ability to do. They're not labeled anything.
Oh.
They had labels like X2.1 and X2.2 with no information about what that meant. So I couldn't do any kind of like interpretation of what they are. So I had no idea whether they were leaving them out were like significant and like in a non-statistical sense, right?
Thank you. All right.
Wow.
So, sorry, I have a question related to that.
Yeah.
So we have 91 the measurements. So evidence measure. So that depends on the song and also depends on the person.
Yeah.
Okay, so maybe the person's response to the clips, maybe.
Yes.
Okay, I see.
Yeah. So for each evidence measure, they had of the 27 per people, they broke the 120 videos up into approximately thirds, and each person did, or like each group of 9 did a third of basically the videos. And so yeah, and the evidence measure was a sum of those 9 people basically. So it went from -9 to 9.
So the values are different for each person. So
the values for each person that is like on that doing that video clip. So like 9 people shared all the same videos. They rated all these like 1/3 of the videos.
Sure.
In each frame, they had their rating, but for each like data line, those strengths for that 9-frame segment were all the same, shared between those, because it was a sum of those individual 9 people.
So it's dependent on the video, but not dependent on the person, because it's a kind of statistics summarized. They're based on the. Okay, I see. I see. Can you explain what are these 16 variables in the slide of correlation matrix? What are these 16 variables?
Yeah. So those are the 15 predictor variables. Where do I? One second. Go back to sharing.
So those are summarized information of those 91 evidence measures, or I don't
Yeah,
know.
so those are the, oops, how do I? Okay, there we go. So let me go to, so they're the 15 predictor variables and the dependent variable, the thing we're trying to depict is 16.
Oh, okay. So 15 variables are
Yeah.
what? So originally we have 98 columns in that data set.
Yeah. So the first two
Uh-huh.
are the only two that really have like only two that I can actually interpret, right? Because they're the only two that the data actually tells me what it is. The first one is the participants' prediction, and the second one is their reaction speed in
then others are
milliseconds. Yeah.
others
The others
some
are just
significant.
evidence variables that I
Okay.
can't interpret because they didn't
Based
tell
on
me.
p-value, you picked this.
Yeah.
Okay.
Based on p-value. There's one other like time measurement, but it wasn't significant because it was just reaction speed in terms of frames. So it's basically just this variable, just recoded.
Sure, I see. Sorry, the last question. So in the results, you compare results between different models.
Yes.
So these are the training error or
test. This is test error.
Test error. How did you test? You split the data set into two?
Yeah. So, I forgot to mention that. Yeah, I split it in 70-30.
Okay, I see.
70 training, 30.
Okay.
Yeah.
Just randomly from the entire
Yes.
rows. Okay. Okay, thank you. Yeah, I think this data set also has some dependence. So it depends on how to interpret the data, but we have multiple measurements, multiple people by multiple video clips. So we have multiple measurements in either of the ways. So sometimes we need some dependence structure we have to model. Yeah, I think you can use, for example, the mixed effects model covered in 6840 to analyze this. Or yeah, you can deal with the factor variables. For example, the individuals as factors or video clips as factors. Then you can analyze the data in that way. Yeah, anyway, so it's interesting comparison. Yeah. Okay, thank you. Do you have any other questions? Okay, so the next one is Michael's presentation. So Michael, can you share the screen?
Yes.
Okay, so you can start.
Okay. So my data, sorry, I'm having issues. Okay. My data shows the birth weight of children based off of multiple characteristics of the mother. These characteristics include gestation, which is the length of their pregnancy, parity, whether they've had a baby before or not, their age, height, weight, and whether they smoke or not. I got my data from kaggle.com. The original data set contains 1,236 observations and 8 variables. After removing cases where a variable was unavailable, I was left with 1,174 observations. I also converted my birth weight response variable to a binary response variable where birth weight was 0 if under average, which the average is 112 ounces, and 1 if it's over average. Here I got the correlation plot. I was surprised to see that height and weight didn't have great like higher correlations, and also surprised that smoking had such a negative correlation. The methods I used to, the methods I used to test models was linear discriminant analysis, or linear regression, or logistic regression, generalized linear regression, and multivariate polynomial regression. Here's my summary of my model, and this is where I use the significance level of 0.05 to remove age as a variable. And then I use the step function to see if any other can be removed, and every other one was significant. I tested each model using contingency tables and the AUC. With GLM, I got an AUC of 0.7534 and an error rate of 25.13%. With LDA, I got an AUC of 0.7531 and an error rate of 25.3%. With multivariate polynomial regression, I got my best AUC of 0.7698 and an error rate of 24.95%. In summary, using multivariate polynomial regression gives us the best model due to it having a lower error rate and higher AUC. And also I ran this from 1 to 18th degree because my smallest unique number was 19. So I ran it from 1 to 18 and got 3 as the best degree. For future work, I would like to do the same analysis on data set containing only the information on fathers and see whether the models fit better. Thank you.
Yes, thank you, Michael. Yeah. So what's the specification of your multivariate polynomial regression? What degree you used? And
I used degree 3. So I tested the, 1 second. Sorry. So I checked the unique length of my 3 variables that weren't binary, and the smallest one had only 19 unique variables. And then I ran that 1 to 18 degree of gestation, weight, and height, testing AIC to get the lowest AIC for the best model.
I see.
And I got degree 3.
I see. And these AUC and the error rates are based on training error. Is that right?
Yes.
Okay. Okay, thank you. So does anyone have questions to Michael?
I've got 2, I think. In the deck you had, did it include anything involving anything like gestational diabetes?
No.
Because that really makes an impact on the size of the child.
Yeah, no, it did not.
Okay, and so you don't know if they actually have it or not, because that's a good flag one way or the other.
Okay.
And the last question, or just a comment question, I guess. I would have been interested if you get a father-mother mix of on that. Be interested to see if you actually can see a correlation between the father and the mother data. Yeah, causing relate. Thank you. I'm done.
Sorry, the predictor is weight and height. Are the mother's weight and height?
Yes, it's so everything's based off of the mother. So whether she smokes or not, her height and weight at birth. And yeah.
I see. So the word regression comes from the fact that the height of the children are influenced by the height of parents. But if parents are really high, like the 7 feet, that does not mean the children is also 7 feet. So like maybe 6 feet 5, but not 7. So basically it goes back to the overall average of the population. So basically the coefficient of parents' height is less than 1, like 0.5 or something. So that's the reason that we say that model as regression. So it regresses, the regresses to the center. So that's the original, the original reason that we say the linear model as a regression model. Okay, thank you. And
I gotta stop.
yeah, yeah. Yeah, I think it makes sense. The model makes sense. Okay, so the next one is the Colin's presentation. So can you share the screen, Colin? Okay, you can start.
Okay, everybody can hear me fine, right?
Yes.
All right, so let me close this out of the way. So I did an analysis on political polarization in the House of Representatives, specifically from 1984. Basically, what I wanted to do was determine the level of polarization present during that year, and I just fit 2 different models, and I wanted to see what we can conclude based on that finding. So I got the data from the UCI machine learning repository at 435 observations. There were 16 predictors and just 1 response being political party. And the predictors just correspond to how each member voted on a certain key issue. 3 possible values for each of those. There was a Y meaning yes, N meaning no, and then the question mark, it basically just means they voted present or they abstained. It's not really an NA value, so we could still work with those. And then obviously the response is just binary. It's a political party. Yeah, and in hindsight, I kind of regret choosing this data because everything was factor and I didn't get nearly as many descriptive statistics as I wanted to, but the code was a headache, but I did my best to make it work. So these are just 3 different bills that were voted on. This physician just kind of means like there's a lot of history involved with these. I don't really know what the issues were at the time. Obviously, I wasn't around. But this physician just means like physician fee freeze. I assume it has something to do with healthcare. This budget is some sort of budget resolution, and then this is like a water sharing project. Under physician, you can see that Republicans heavily. So I transformed all of my votes. So 1 ended up being yes, 0 was a question mark, and -1 was a no. So you can see Republicans voted heavily in favor of this physician fee freeze, and Democrats voted no. And then it was the opposite for budget. And then water was pretty split amongst both parties. And I actually found it pretty interesting that the proportions are pretty much the same across both of the parties. Like almost the same amount voted yes, almost the same amount voted no. I thought that was pretty interesting. So first I divided the data into test and training sets. I did 50-50 approximately. It was an odd number, but and then I just fit an LDA and support vector machine to the training sets to evaluate the test performance. And then I was comparing both of the 2 models just by their cross-validated error. So this is what my LDA looked like. these are all of the predictor variables here. So there's infinites, there's all types of other things. But you can see just based on this that, you know, the votes were pretty heavily split among most of the issues. The only one where both of the parties seem to be in somewhat of an agreement was this to provide aid to South Africa. Maybe I'm wrong, but that might have been during maybe during apartheid or something with Nelson Mandela. I don't know. I'm not a historian, but and the coefficients of linear discriminants. And then I plotted the LDA here. If I'm interpreting this correctly, it seems that this distribution is, you know, low values favor Democrat, high values favor Republican, and they seem to be pretty evenly split. There's not a lot of overlap here, assuming I'm interpreting this correctly.
Yeah, I think you're right.
And then the support vector, did I miss a slide? I don't think so. My support vector machine, I wish I had a lot. I wish I could give more detail on this. The intricacies of the model are kind of beyond me a little bit, but I have 20 support vectors, just 2 classes, and this was the model matrix. This is just a brief overview of what it looked like. In total, there was nearly 14,500 parameters, probably plus 1 intercept as well. I chose for my cost function equal to 2. I kind of just ran through a few different values, and this ended up maximizing the area under the curve for the ROC curve, as well as minimizing the cross-validated error. I tried a few different things, and 2 ended up pretty much being the best there. I meant to mention beforehand too, I chose these 2 models simply because I had anticipated that these would be pretty evenly split. And I mean, these models perform well under those circumstances. The test performance for the LDA, here we just had an error rate of 5.5%. So it looks like we have a pretty good performance rate. And then, you know, the area under the curve was really close to 1. And so this model was very effective in performing the analysis or predicting the political party affiliation. And then the SVM, the area under the curve was slightly lower, but the error rate was actually better for the SVM. So in the long run, just based off the ROC curves, maybe we would expect the LDA to perform better, but after doing the cross-validated error, I did 5-fold and 10-fold, each of which were lower for the SVM than they were for the LDA. So just based off of these 2 things, you know, it might be a little difficult to determine which is better, but more likely the SVM is a little bit more effective. So given the ease of actually predicting the affiliation, pretty much concluded that there's a high level of political polarization during the time. But that's assuming that the data was chosen without introducing, you know, a lot of bias in the results. You know, whoever chose these issues might have just chosen issues that were where the House was heavily divided. So of course, we're going to conclude that there was polarization based off of that. But assuming they were unbiased in their selection, then it appears as though the House just kind of votes along party lines, which, I mean, that shouldn't really be a surprise. And then just maybe some additional analyses or benefits of this study. This first one was something that I had considered to do, but I just simply didn't have the time to do it. But, you know, basically just perform the same analysis for today's Congress or even the Senate. And just, you know, see how they compare, whether or not polarization is more prevalent today, or if it was then, maybe they're the same. I would expect that it probably would be greater today, but that's just my presumption. And then there's also this inverse analysis, what I call it. Maybe just given the political polarization, you kind of predict whether or not a bill will actually pass through the House. in assuming that there's actually high level polarization present, then, it's really just going to come down to whoever holds the majority. So maybe if they implemented something like this, the government would actually be incentivized to be more productive, but that's a dream. So, but that's all I have. If anybody has any questions.
Have you tried other kernels for support vector machines?
No, I actually didn't try any of the other kernels.
I see.
It kind of crossed my mind for a moment, but I figured with such a high performance for the linear kernel,
Mhm,
I didn't think it was going to make a big difference.
mhm. Yeah.
I should mention too, I wanted to actually plot support vector machine over the data, just see what it looks like, but I don't know. R was really not cooperating with me. I think it had something to do with the fact that all my data were predictors. I spent hours trying to get it to work and nothing was going for me. So I wasn't able to include that, unfortunately.
Yeah, so I think it's reasonable that if we considered a small data size, probably, not too complicated boundaries are sufficient. But one thing is support vector machines with linear kernel and the linear discriminant analysis are really similar because both are linear. But the support vector machine performs better. And probably the reason is error functions are different. So support vector machine basically penalize the absolute value of error. So basically the distance is the cost, right? Then LDA basically penalize the squared error. So that means probably there are some extreme observations or outliers in the data set. So support vector machine may be more robust. So that may be the reason that the SVM consistently performs slightly better. Yeah. Okay. Does anyone have questions?
No, I thought the presentation was fairly clean.
Yeah, it's very easy to follow. So compare two methods and they clearly compare the training error and the test error by cross validation and the interpretation. Yeah, it's very clean.
Thank you.
Yep. Okay, so I think we finished so the last presentation is the Luke's presentation. So can you share the screen?
Yeah. Okay. Oh. Okay, I should.
Yeah, the green button at the bottom, probably.
Yeah.
It depends on maybe
Oh, there
operating
we go.
system.
There we go.
Yeah.
Yeah. Okay.
Okay, you
yeah.
can start. Yes.
So yeah, so my project is on the English Premier League. I'm going to call it football, but you call it soccer. But yeah, so the data set is from the 2020 to 2021 season, and I cleaned the data so that because I'm looking for what predictors can affect how many goals a player can score. So the players who are forwards normally score the goals. So I thought it would be best to just focus on those. So I cleaned the data so it only had the forwards on there. And then it has these variables using as predictors. So I have goals scored in that season, the age of the player, number of assists. So assist is just when the person, if I was to get an assist, I would pass the ball to the person who scored. XG, that is a new thing that's come in the last few years, where it is a statistic that measures how good of an opportunity it is for a player to score. So if you are 1 yard out from the goal, your XG for that will be a lot bigger than if you just kicked it from very far away. And then also number of minutes played during that season. Just see if you're on the pitch longer, if you score more goals. So there was 96 players in this data set. So I'm just going to help you sort of understand the variables against how many goals scored. So I just did some scatter plots. So with XG, for example, it's clear that if you have a higher XG, you are more likely to score more goals across the season, with coefficient correlation being 0.75. It's high, and there's a couple of outliers in the top right with Harry Kane and Mo Salah, just because they're just the best players basically. And then also Heung-min Son, he scored a lot more goals compared to his XG as expected. And then same for assists, but the correlation isn't as big. It's a lot more scattered, which suggests that isn't as clear. Minutes played, that's again the coefficient correlation is stronger. So that suggests that they're related. And then age has pretty much zero. It doesn't make any difference. So I started off with a linear regression model, and the p-value at the bottom is obviously very small for the f-test. So that shows that there is a significant linear relationship between goals and the predictors. But as you can see, the value for age is 0.239, which is high. So that suggests that age maybe, and it comes back to the scatter plots, that they aren't related. So then I went on to GMs to try and see if that had any effect. And as you can see, the degrees of freedom there for age and assists are 1, which shows that it's very similar to a linear relationship. And then the R squared of 0.86, oh, I wrote that down, 0.83, sorry, and then 85.6 for the deviance. That's high, so that means the model seems to be a good fit. But as again, if we come back to the age, the p-value of 0.352 is again high. So that's just supporting maybe the fact that age doesn't have any sort of effect on goals. So I sort of decided to compare the GAM model to the linear regression. So the AIC for linear model was 440, and when we did that for the GAM, it was 423, which, as it's been lowered, it means that the GAM model is better and more accurate. So I did it, and then I did an ANOVA one, and the p-value for the GAM is incredibly small, which shows that once we've incorporated the non-linear relationships into the model, then it actually improves it and makes it more reliable. Then I went on to KNN. I did the training and test set. I did it randomly split, 70% for the training and the other 30 for the test. So the night I actually looked this on Google to find like the optimum KNN, and they suggested the square root of the number of observations. So that was 9.8. So I decided to take 2 of 1 of k equals 9 and 1 of k equals 10. But so the k equals 10, the accuracy was 20.7% compared to 17.2. So k equals 10 is obviously better, but they're very low accuracies, which suggests that the KNN model probably isn't the best and most reliable to use. So yeah, the results is the GAM is definitely the most convincing for using the predictors to guess how many how it affects how many goals a player will score, with KNN being by far the worst. And then coming back to the age, it does suggest that it maybe doesn't, but this is just sort of using my knowledge of football. That so I decided to do a cumulative bar chart of just this data set, and obviously the age of 23 is high, and then 26 is low, but it sort of follows a normal distribution curve, which I know for players, they normally do peak around 27 or 28, which would make sense that you would score a lot more at that, and then would score less as you got older. And then in this data set, the top 4 goal scorers were 26 to 28 years old. So I think if I was going to do like a deeper analysis, there's bigger sample size. So let's say I would do over a 10 season span. I think that coming back to that bar chart, I would maybe show that age does affect goals scored, but not quite how the other predictors do. And then also I would, with obviously only using 4 variables as predictors, it would be good to expand that. And then use maybe even if a player is left or right footed, or the number of touches they have per 90 minutes. See if they have more touches, they score more goals, and then a few more. And then also a big thing is if you play for a better team, that you probably get more chances to score, which is something I would like to look into as well. Thank you.
Hey, thank you, Luke. So do you have any questions?
I have one. Back on the bar chart, Luke.
Yeah.
Did you just sum all the ages, or did you normalize that so that you had, if you had, my assumption would be if you had 15, 20, 23-year-olds and 1 27-year-old, and you sum them, you might find that to be a little bit different in terms of the numbers.
Yeah, that's obviously a problem with the small sample size that I do have, but I did just do that as sort of a test to see if it did follow it. But yeah, that is a problem with that. I did choose, yeah.
Probably the thing that might have helped would have been to figure out how many you have of each type, each age group.
Yeah, and do an average, yeah.
Yeah, if you'd, I don't know what the numbers would have done, but that just stood out to me as being potentially a problem.
Yeah, that makes sense. Thank you.
No problem.
Yeah, so can you show the earlier slides, the scatter plots, maybe the first, maybe
yes,
maybe third one may be the best. Yeah. Yeah, so you can see we have some nonlinear effects, right? So if we see the right 10 observations, the most observations are above the trend line. So that means the linear model does not capture the entire picture. So that's why the GAM, the generalized additive model works better. Yeah, I think that happens sometimes. I think there, the real estate websites have forecasted price for each house, and that forecast is good for majority of houses. But if some houses are really large or really small, really old, then the price is not really accurate. So basically, because of this kind of effect. So I think you are good that you see the data, and you can see that the GAM works better than linear model in this case. Yeah, and another thing I want to mention is can you show the KNN slide?
Yes.
Yeah, I think that this wasn't really it does not make much sense to me, because you are doing the regression problem. So KNN also has to be applied as regression, but you reported accuracy. So probably this was, I don't know. So accuracy was calculated. That is, the KNN is applied for classification problems. So
Yeah.
I think it's better to apply the regression problem. So of course, the number of goals are discrete, so you can apply the classification, but I think the regression more appropriate to compare it with linear and generalized additive models.
Okay.
Yeah, sure. Okay. Do you have any other questions? Okay, so I will upload today's video as soon as possible, and you can comments on it. You have already seen all presentations, so you can comment on it and vote for the best 3 presentations. For example, maybe one from the first day, one from the second day, or whatever. So just the 3 presentation overall among all presentations. Okay, so I think that all presentations are successful. Of course, you prefer some presentations better than others, but yeah, I think there are good variety of presentations that all students made. Okay, so do you have any questions about the class or any course materials or?